Oh, so hello. So we're back to band properties now in section 7.3. And what we're after is expressing wave packets in the newly defined bands. And from there we'll define effective masses and the concepts of electrons and holes. All right, so let me start from the formulation of a wave packet. I mean, the simplest way to think of it is you can start out with adding two different plane waves to each other. So here's one plane wave that satisfies Schrödinger's equation and the propagation in the considered bands here. And here's another wave. It looks very similar. It has slightly modified energy and slightly modified momentum. And you add those two waves together, and you can pull out one of the coefficients that is the original wave in the first line. You can also, if you do signal processing, or you could call that a carrier frequency. And then you have two components to that, this component here and the larger component here. And you have a delta K as a propagating coefficient in space and a delta E as a propagating coefficient in time. So you have an object that has a higher frequency component on the left, the carrier, and a lower frequency in space and in time, that is a signal. All right, so you might be familiar with that already in other contexts of electrical engineering. So you can add these two waves that at some point T1 add up very well, and they build a wave package. And at some other time, T2, these two waves add up constructively at another time and space. So you have a wave package that propagates. And of course, you define normally a package out of many more components. So here you have a simple example of just two components. But let's carry this forward a little bit more. So here is your expression of two waves that are summed up. Again, you have a carrier component here and a signal component written in here. And the signal really propagates in space. So this is now your signal component, e to the I, and some constant that propagates in time and in space. So we're looking at this coefficient, delta xk times delta x times delta k minus t delta E over h bar. And if that is forming a constant, that is how the package is propagating in time and in space. So let's imagine that we construct this package in this form, and we take the time differential of this package. We can, if that is a constant, obviously this ultimately needs to sum to 0. But we can also take this expression here and take the time differential. So if we take the time differential of this, we know it's delta dx dt times delta k minus delta E over h bar, and that needs to be 0. So we can resolve that here into delta x over delta t equals 1 over h bar delta E delta k. All right. Now, dx dt you can also define as the velocity. And if that's the case, then you have dx dt, or the velocity, as 1 over h bar dE dk. All right. Now, if we relate that back to classical mechanics, we can talk about a momentum, which would be h bar k, and we can define the force as dp over dt, or F equal ma, and we suddenly relate a wave property to a momentum. And we can do this here as well. So now let's look at the acceleration of this particle. That would be dv dt. And so we're going to just take the differential, plug this guy in here. And we get 1 over h bar d dt times dE dk. All right. Now, here's a well-known trick that if you do a trick multiple times, it becomes a method. Let's introduce a coefficient 1 into the system, and that coefficient 1 is this guy here. We're going to take the differential versus k of h bar k, which is h bar, divide by h bar, and that is 1. Now, you can rearrange this term and rearrange the differentials where you end up on the far right with dh bar k dt. And that you can identify again over here with this expression from up here. That is the differential of the momentum. And the differential of the momentum is 1 over m star times f. So you can define something conceptual as m star as being 1 over h bar squared d2e dk squared. All right. Now, we have this expression where we can define the effective mass of this particle or this wave package that is propagating at a certain velocity inside our bands. All right. Now, interestingly enough, if you look at the differential of the band, of the red band here, you see at k equals 0, you have 0 velocity, and you have a positive value of m star. And you also see that inside the band, you have an effective mass, 1 over m star, that is k dependent. Now, that's an interesting concept in the sense that this particle changes its effective mass. We often just deal with energies that are close to here, where the mass is roughly constant in the ideal world, but we'll also explore, especially in nanoelectronics, areas where the effective mass changes significantly as a function of momentum. All right, the other band is bent in the other symmetry direction this way. Maybe I should not write red over blue, but you compare the blue line here, and you find that the effective mass is actually negative. So this is a particle that has a negative mass. What that means is really, is you have F equals ma. If you push it with a vector in one direction, it actually moves the other direction. So that's how you can think about it. So that means this particle behaves opposite of the normal classical particle in terms of its force. This is really the essential definition of a hole, and we'll talk more about what holes mean in band structures, etc. in a little while when we talk about doping, etc. But you can just think about electrons sitting here, and holes would be sitting here, and they behave opposite in their behavior of electrons. All right, this concept of an effective mass is not an essential piece of band structure. There are actually materials where an effective mass really can't be defined. So if you have a dispersion that is linear, and graphene and other 2D materials have dispersions that are linear or have this Dirac-like dispersion, what you find is that the first differential you can still take, and there are bands that are in this shape and form where the velocity can be defined, but you cannot really take a differential across this vertical step here. So the effective mass really is ill-defined, and it doesn't make sense to build an effective mass for electrons in graphene, for example. So it's ill-defined, but you can still deal with the integral quantities that are relevant. And the integral description of momentum and position of these wave packages are still meaningful. It's just the effective mass doesn't make a whole lot of sense to use. So effective mass is actually not a critical physical property, but for many semiconductors, it helps us understand the behavior of electron flow and hole flow. So as I mentioned, graphene is an example where the effective mass is not really well defined. Okay, now let's look at electrons and holes a little bit more carefully. Let's consider this band structure as shown here on the graph. There's electrons that are filling all the states below the Fermi level, and we consider the bands that are above, but there is no electrons in it. So if you don't have electrons in the band, then you don't have current, because there's no carriers that could carry the current. Now, let's look at the filled bands below. So we would want to sum over all the electrons that are moving at a certain velocity over all the filled states. If you spread the left and the right going states, so you sum over the left and the right going states, you basically have in symmetric bands like this a balance in all the particles that are going left with all the particles that are going to the right. So if you have inversion symmetry in the system where the number of states in the plus and minus direction are identical, and you need to, of course, follow the Pauli exclusion principle, then all the states going left are equal and opposite, balanced by all the states to the right. That means a full band cannot carry current either. So you have lots of electrons in there, but there's effectively no current that is being carried, no net current. All right, so let's look at partially filled bands. So what we consider here is we find a mechanism to elevate some of the electrons from what we call the valence band into the conduction band. And let's just imagine we found a way to do that, and we'll discuss the details on how to do that later. We can do that by optical excitations, thermal excitations, and we'll talk in a lot of details on doping and a little bit of thermal excitation. So let's consider this band where we're looking at the filled state in the conduction band in red. And now we're going to apply a field, an electric field, to the structure. What that does, it moves the electrons in their k-space. Some electrons are more moving into one direction over another direction. So you find an imbalance in the dispersion. And that means overall, there is no more balance of left and right going electrons, and therefore you have a net current that will flow. Now, similarly, for the holes that are the empty states, you will find an imbalance as well, and you will have an electron flow in these hole bands. And what you can do is, as a methodology, you can sum or represent the electron flow in this valence band here by summing over the filled states, or you can, which is a lot of work if there's a lot of electrons in there, or you can make your life easy by distinguishing that between all the states and the empty states, because the number of empty states is actually much smaller than the number of full states. And with that, it's useful to define holes, because the sum over all the states, all the velocity of all the electrons is 0. So it's much easier to talk about summing over empty states in the valence bands, and that is what we call holes. The holes are the empty states in the valence band. And what you have is electrons moving at a certain velocity in the conduction band, and holes moving with a certain velocity in the valence band, and holes are the lack of electrons at specific states. So now let's reinterpret a little bit the effective mass in that context. We had defined the effective mass as the second differential over energy in these dispersions. And so we can take this differential, and already we had indicated that this effective mass inside a band changes its values. It even changes signs. And it means these wave packages are not free particles. It's not the free electron mass. It's a function of K. It can be negative and positive in the same band, which is kind of surprising. If you looked at other literature where you just consider one constant effective mass. And it can vary significantly across different bands. So here you saw in red the dispersion being quite different from the blue band and being quite different from the green band and being quite different from the orange band. And we had seen that bands at the lower energies look flatter, not as strongly curved as the upper bands, as the orange band, and there's some interpretation for that as well. Let's interpret those a little bit, but let's focus on the bands that are really critical. So for transport, some bands are more important than others. For example, some are always full, so they don't contribute to transport and electron conduction, so we can take those away. Some are always empty because they're so high in energy we can't get electrons there, so we can forget about those. So we typically deal with what we call conduction bands, so typically the lowest conduction band, and the valence bands, and there's typically 3 that are involved here in the sketch. For the one-dimensional periodic case, it's just one valence band. All right. So in here, we can do a little bit more interpretation where the effective mass of the conduction band at close to k equals 0 is positive, and it has a certain value. And it is negative for the holes at k equals 0. And as I mentioned before, we often, for large structures, focus on a K range that is very small, where the effective mass is then roughly constant. And that is how we typically think of electrons in the conduction band and holes in the valence band as having a constant mass. So what happens is effectively that electrons, quote unquote, fall to the bottom of the conduction band. Even if we somehow kick them up in here, they eventually really fast fall down and accumulate at the bottom of the conduction band. And similarly, holes start to pool up or float on the top of the valence band. So those are the particles we typically consider in the semiconducting devices. And we consider constant masses at these very narrow energy ranges, or K ranges, where the electrons and holes are gathering. All right, so let me conclude this section here on band properties and on the periodic potential. So calculation of the Schrödinger equation in a square potential well with periodic boundary conditions is reasonably easily done. It's called the Kronig-Penny model, and you can derive fundamental band properties in solids from it. We have compared that to transmission coefficient-based methods and seen that we get extremely similar results. Conceptually, they're the same. And in both cases, you depend on introducing a methodology to reduce your infinite system into a finite system. The finite system here on the periodic potential is that you consider a period length of n, capital N cells, where n is an arbitrarily large number, and it shows up in the discretization of your crystal momentum space. What we find is that electrons can only sit in specific bands, and we use effective masses to summarize the properties of these bands. These effective masses are typically only meaningful at the top of these valence bands or the bottom of the conduction bands for most of the work that we'll do in this course. If you're working in nanoelectronics, you'll find that these masses vary as a function of k, and that becomes really relevant. But for the fundamentals of the understanding of these semiconductor devices, we can assume that these masses are going to be constant. And then one key element is, again, we typically focus on two bands, the conduction band and the valence band. And the valence band could be three bands combined, but that hasn't emerged yet into the periodic potential that we looked up so far here. So thank you.